Ladies and gentlemen, 6.5 hours ago, the sun rose over Stockholm. It is fair to say at this point that all of us are ready for an invited talk. My name is Vincent Conater. I work in the intersection of economic paradigms and AI. There is a complementary community in the theoretical computer science field that also thinks about economic theory. Together, these two communities span a very nice spectrum from theory to practice. Our invited speaker, Nicole, is primarily on the theoretical computer science side, but she doesn't just do theory for theory's sake. She thinks carefully about the importance of her models, and she collaborates broadly with people across the spectrum. Her list of co-authors on DBLP counts 127 co-authors, people from across the spectrum, and many of them here today. For example, Milind Tambe, who will give our McCarthy Award talk tomorrow. And all the way at the bottom of the 127 people, in last place, there's me. I don't know how I ended up in last place, but let me just say that I very much look forward to, at some point, work with Nicole again, and it's not only to get out of last place. Nicole received her PhD, and I think all her other degrees from MIT, did a postdoc at Microsoft Research, and did another postdoc at Amsterdam's CWI Center for Mathematics and Computer Science. She then joined the faculty at Northwestern University, and eventually returned to Microsoft Research. Please join me in welcoming Nicole.
Hi, thanks so much for that introduction, Vince. I challenged Vince to be amusing, and I think he did a great job. So today, as Vince mentioned, my research area is the intersection of computer science and economics, primarily on the theory side. And what I'm most interested in the context of this field is market design. So markets, at their essence, are algorithms, which is my specialty, so why I'm able to study them effectively. They're algorithms that interact with individuals to produce and/or allocate scarce resources. For example, you have the ride-sharing platforms like Uber and Lyft, which at their very core are algorithms that compute prices in response to supply and demand in order to recruit drivers and allocate rides to riders. Platforms like these, commercial platforms like Uber and Lyft, have as their primary objective the generation of revenue. But what I'd like to focus on today is markets whose primary objective is to maximize the value of society. So to start, I'd like to point out that even if your goal is to maximize the value of society and you have no objective of raising money, it's still very useful to use money as a tool in the design of your market. Think, for example, about this setting. We have a painting, and we'd like to allocate it to one of three buyers. The buyer on the left has a value of just under $700,000 for the painting. The buyer on the bottom has a value of $300,000 for the painting. And the buyer on the top right has a value of $700,000 for the painting. Now, there's three possible allocations here, right? I could give the painting to the buyer on the left, the buyer on the bottom, or the buyer on the top. And among these three allocations, the one that maximizes the aggregate value to the buyers is the one that gives the painting to the buyer on the top right, because that's the buyer who values it the most. So how can I design an algorithm which is guaranteed to give this painting to the buyer who values it the most? I could try to just ask the buyers what their values are for the painting, but then, of course, everyone is going to inflate their value in an attempt to win the painting. So an alternative is to use money to basically fact-check the reports of the buyers and give some sort of proof of concept that they actually had the value they reported for the painting. One way to do this is through the use of an ascending auction. So the auctioneer will call out a sequence of raising prices, starting with, say, $200,000, and as the prices raise over time, the buyers will drop out of the auction when the price exceeds their value. So here the price has raised to $400,000, and the buyer with the value of $300,000 has dropped out of the auction. The auction will terminate when only one buyer remains. So here we see that the price has reached $687,750. only the top right buyer remains, and so the top right buyer is awarded the painting and is required to pay $687,750 for it, which, by the way, is the price for which this painting sold at the Christie's auction in New York City. So the very beautiful thing about this auction is that we ended up allocating the painting to the buyer who valued it the most. This didn't necessarily have to happen, right? The buyer on the left there didn't have to drop out of the auction when the price exceeded her value. She could have stuck around trying to outlast the buyer on the top right and thereby win the painting. But notice doing so would incur a cost for her because she'd end up paying an amount that's $700,000 for the painting, which is higher than her actual value for it. So it would be a bad deal for her. And this type of reasoning allows us to conclude that when individuals are acting to maximize their personal gain, the market will end up allocating the item to the individual with the maximum value. And notice that the use of payments, the use of money, was the key tool that allowed this algorithm to produce this outcome. Now, this algorithm is not specific to art auctions or even single item auctions. In fact, in a very general sense, variants of this auction can maximize the value to society in pretty much every market that I'm going to discuss today. So why then, you might ask, am I interested in running markets without money if we have this beautiful algorithm that uses money to get the optimal outcome? And there's several reasons I might want to do this. One is feasibility. It could be that it's simply technologically or financially infeasible for the market to pay or charge the market participants. One example of this is the market for road traffic. That is, which cars get to drive on which roads and when. Now, with current technology, it's very hard to track where every car is at every point in time, which is the information we would need in order to optimally charge payments to induce the optimal routing of traffic. Some countries are approaching this sort of technology. Singapore is a great example. But it's still technologically challenging. And so instead, traditionally, we've used congestion instead of money to route traffic. In other words, instead of charging users or drivers to drive on high-demand roads, we can simply count on drivers to avoid traffic jams. So does this cause us to have the optimal routing of traffic? Well, we'll see. Another market where it's potentially difficult to charge or pay users for participating is the market for online content. Here I have in mind online platforms where users provide data to the platform, and then the platform generates value out of the data that the users have provided. So how can the platform incentivize the users to provide data? Well, many of them listen to the advice of Napoleon Bonaparte, who famously said, "Give me enough medals and I'll win you any war." And so what they do is they create medals, or since they're online, virtual medals, i.e. virtual rewards, that they hand out to users in exchange for the user contributions. So instead of paying users money to provide content, they pay them with these virtual rewards, which in essence confer fame upon the users for the content that they've provided. Another reason you might want to avoid using money in the design of markets is repugnance. So one example that comes to mind immediately is the market for presidents. Many societies deem it morally repugnant, or at least incredibly undemocratic, to charge users to vote for presidents. And so instead of charging users money to participate in elections, we allocate to users votes, and then we ask them to signal their preference among the candidates using this scarce resource, i.e. their vote. Another market where we've decided it's repugnant to use money is the market for schools. So education is a basic human right, and traditionally, so therefore we don't want to charge people for access to education. But traditionally, you went to school in the neighborhood, at the neighborhood school, to the school that's closest to where you lived. And this enabled rich people to buy access to education by moving into wealthy neighborhoods with good schools. Now, in many cities in recent decades, the city governments have tried to circumvent this issue by giving students the opportunity to attend any school within the city boundaries. But of course, the seats at the public schools are a scarce resource. And so the question is, how can I allocate these seats to the children that value them the most? And what we'll discuss today is a school choice system that uses raffle tickets to allocate seats to school children in a way that maximizes the value that the children receive for the schools they attend. That is, instead of charging money to infer the values of the children for the different choices of schools, we're going to offer the students varying levels of risk, which will then serve as a metric for how much they value each school. So these are the 4 markets I'd like to discuss today: the markets for road traffic, the market for online content, the market for presidents, and the market for schools. And the theme of this talk, what I'd like you to take away, is that in markets such as these and many more, you can use alternatives to money to serve as a metric by which we can measure the value of the outcome to the society and thereby optimize the value of the chosen outcome. Let me start with the seminal example in this field, which is the market for road traffic, in which we're going to use congestion instead of money to select a high-value outcome. This is a map of Seattle. Seattle is the home of the mothership of the company I work at, Microsoft. On the left, we have downtown Seattle, where all the cool kids live. And on the right, we have the east side. In particular, Redmond is on the upper right of this map, and that's where most of the Microsoft offices are located. Now, you can see that to get from Seattle to Redmond, you have to cross this lake, and there's essentially just 2 options for doing so. You can either cross on 520, which is the highway to the north, or I-90, which is a highway to the south. And this picture shows the congestion of these routes during rush hour on some particular day. And so it raises the question for us of how well does that road network route traffic? Were those traffic jams you were seeing in the map unavoidable in some sense? Was everybody experiencing the optimal delay in their commute to work? To answer that question, let's first study an idealized setting. Here we have a 2-road network, Seattle on the left, Redmond on the right. On the north, we have the Highway 520, and on the south, we have Highway I-90. Now, let's assume, for the sake of argument, that the delay on 520 is proportional to the use. So how long it takes to cross that bridge is a function of a linear function of how many drivers choose to use that bridge. Whereas I-90, perhaps the road is larger, it has a different technology, the delay on I-90 is always the same, no matter how many cars are on that road. To be more precise, let's assert that the delay on 520 is 60 minutes times the fraction of cars that decide to drive on I-20, whereas the delay on I-90 is 60 minutes, regardless of how many cars choose to drive on I-90. Now, imagine that you're a commuter in this world, and think about how you would choose to get from Seattle to Redmond. Well, if you take I-90, you're guaranteed a delay of 60 minutes. But if you take 520, then your delay could be at most 60 minutes. And so clearly, your optimal strategy here is to take 520. And everybody does that. And so everybody travels on 520, and hence the delay for each person on 520 is 60 minutes. OK, that's great. This average delay is 60 minutes in this equilibrium. Is there a better outcome here? Could we, if we were a centralized controller, if everybody had a self-driving car and we could dictate where they go, could we achieve a lower average commute time for our citizens? And if you look at this, it seems a little wasteful to not use I-90 at all. In fact, you could move half the traffic off of 520 and put it on I-90, and those people wouldn't suffer at all because they anyway had a commute time of 60 minutes. And the remaining traffic on 520 has a drastically reduced commute time of 30 minutes. And so the optimal routing here would split the traffic 50-50, inducing an average delay over all the commuters of 45 minutes, which is significantly less than the 60 minutes that they experienced in the equilibrium. So this is just an example, but there's a very beautiful result in this field, which tells us that this is actually the worst case example. For any road network with linear congestion, the worst-case average delay in equilibrium is at most 33% more than the optimum. So without using money, we're able to achieve a near-optimal average delay. Now, of course, with money, we could induce the optimal delay, and in fact, these routes in Seattle now have real-time traffic pricing, so there's tolls on 520 and I-90, but it's comforting to know that even without money, we aren't suffering too much, because this congestion provided enough incentive for the drivers in equilibrium to route almost optimally. Let's turn now to the market for online content, a little closer to what I do at Microsoft. So in online content, we can see that many websites are replacing virtual rewards with, are replacing monetary payments with virtual rewards. I have in mind platforms like Twitter, Reddit, Yelp, TripAdvisor, Stack Overflow, Amazon, and all of these websites, they generate a lot of value for society. And the primary driver of that value is the contributions of their user base, the reviews that are written on TripAdvisor, the questions and answers that are posted on Stack Overflow. Which leads us to the question of how can this online ecosystem incentivize high-quality content on the part of the user base? Well, as anyone who's spent any time on the internet knows, what internet users covet highly is their 15 minutes of fame. And so these websites have developed ways to use fame to pay users for their online content. There's two ways they do that through the use of virtual rewards. The one primary scheme is badges, which are earned if the contributions of the user pass some threshold on the website. So, for example, TripAdvisor offers a badge, which is called the contributor badge, if you submit at least 10 reviews. Here, you could imagine we have 3 users of the website, Jackie Kennedy, Marilyn Monroe, and Judy Garland, and perhaps all of them pass this threshold of 10 reviews, and so they all receive a badge, a gold star. And this confers some fame upon them because, hey, they have a gold star. But it doesn't really let them distinguish themselves from one another. An alternate scheme that provides incentives to distinguish yourself from more strongly from the other users is leaderboards. So leaderboards often have a contribution cutoff. These are used on Amazon, for example, and for any user that provides enough reviews, the users are ranked in order of the number of reviews that they provide. And so in our example, perhaps Jackie Kennedy provided the most reviews and so got the top position on the leaderboard. Marilyn Monroe provided the second most reviews, and Judy Garland maybe wrote some reviews but didn't make the contribution cutoff and therefore didn't make the leaderboard at all. So this raises 2 questions in my mind. One is, do users even respond to these rewards? Is this working? And if they are responding to these rewards, how do they respond? Once I understand that, I can start to ask, how would I optimize a system if I wanted to maximize the number of contributions? Should I use a badge system? Should I use a leaderboard system? What should the contribution cutoff be? In answer to the first question, we see that users do, in fact, respond to the incentives of virtual rewards. This is data that's drawn from Stack Overflow. They took all the users that won a badge called the electorate badge during the course of the experiment, and they lined up on the x-axis the days relative to when that user won that badge. On the y-axis, we have the total number of actions that the users performed in aggregate on each day relative to when they won the badge. Now, the electorate badge, so here we have 4 types of actions. The green line is for voting on questions. The yellow line is for voting on answers. The red line is for asking questions, and the blue line is for answering questions. And so, try to guess what the electorate badge is rewarding. Right? It's pretty obvious from this plot that the electorate badge is rewarding people for voting on questions. And so you can see that there's a very strong incentive to vote a lot on questions when you're getting close to winning the badge. This indicates that people do have value for this badge. They're changing their natural behavior when they are close to winning the badge because they're trying to get the badge. Okay, so how might we want to optimize this system, given that people are responding to these rewards? Well, in order to answer that question, we have to make some assumptions about how people respond to the rewards. And so I'm not going to discuss exactly what my assumptions are, but I can, no matter what people are doing, you can see that if you have a single badge, there's not really any incentive for a user to contribute more than the contribution of the badge cutoff. Okay, so users for whom it's very hard to make contributions, maybe English isn't your native language, and so it's hard to write a review on Amazon in English. Those users probably won't make any contributions. But so long as a user has at least some ability level, they're going to make contributions which is equal to the cutoff for the badge, and they have no incentive to do anything more. The number of contributions that the website receives as a result is the area under this red curve, which for the parameters I've chosen is 15. An alternate virtual reward system is this leaderboard with a cutoff. In the leaderboard with a cutoff, maybe the cutoff is different, and so users that are a high enough ability perform just enough to reach the cutoff. But then they compete within each other to perform even more contributions because they value being on the top of the leaderboard. And so as a result, the total number of contributions for the parameters I've chosen is 20, the area under the blue curve, which is slightly more than the contributions we received from the the single badge mechanism. So how can we optimize these contributions? And one observation that's been made in the literature is that there's an pretty much direct analogy between these reward mechanisms that maximize contributions and a particular type of auction called an all-pay auction, which maximizes revenue. And these all-pay auctions that maximize revenue are very well understood in the mechanism design literature. So we can use this analogy to help us maximize, design virtual reward systems that maximize contributions. And what we find is that the optimal design is a leaderboard with a cutoff. So this intuition that forcing high-performing users to compete with each other maximizes rewards is a good one. But that cutoff is going to depend on the ability distribution. And it's not very robust to the assumptions of how people respond to the incentives for fame. So instead, we also consider approximate mechanisms. And we can show that constant number of badges is going to produce a near optimal number of contributions, so long as fame exhibits diminishing returns. That is, people have value for contributing to the community, but they don't necessarily need to rise to the very top. Things like maybe websites like Wikipedia, for example. In contrast, when fame exhibits increasing returns, that is, you have a high value for actually winning in competitive settings, like maybe the Netflix challenge, then a full leaderboard is almost optimal. So I'd like to move on now to the market for presidents. Here, we are going to use votes instead of money to try and resolve the market, to try and elect a president that's good for the market. And you might ask, our current elections, are they giving us the leaders we deserve? Are they giving us the leaders that are best for our society? Well, of course, that's going to depend on the voting rule that we use. So can we design a voting rule, a way to aggregate the votes of the citizens in a way that's going to elect a highly valued candidate? Now, most democracies use some variant of majority rule. Let's imagine that there's two alternatives. We'll call them the elephant and the donkey. And so we have two alternatives, and each person is given one vote, and they have to pick one of the alternatives to vote for. Now, it can be that a majority of the citizens prefer the elephant to the donkey, in which case the elephant will win the election. But notice that this will happen no matter what the strength of their preferences are. So it could be that the minority that prefers the donkey has a really strong preference for the donkey, whereas the majority that prefers the elephant has a somewhat weak preference for the elephant. In such a setting, it could be more optimal in aggregate over the population to elect the donkey, even though a minority of people prefer the donkey. But majority rule doesn't do this. So instead, Majority rule elects the elephant. So instead, a recent proposal has entered the arena, which is quadratic voting. Quadratic voting asks you to buy votes with money. So there's that problem, but we'll deal with that in a minute. So if you want to buy V votes, I'm going to charge you V squared dollars for that. This is a quadratic function. Buying more votes is much more expensive than buying fewer votes, right? Increasing marginal returns. So now what's this going to do in our example here? Well, the majority, who's kind of indifferent between the two candidates, isn't going to be willing to spend very much money on voting for the elephant. Whereas the minority, who feels very strongly about the donkey, is going to spend a lot of money voting on the donkey. And so the donkey, in aggregate, you could imagine, will get more votes, and therefore the donkey will win the election in this example. And in fact, this is a very general result. In two-party elections, we can prove that quadratic voting is going to elect the candidate that maximizes the aggregate value to the society. The reasoning is so elegant that I can't resist presenting it to you. The idea is that, well, each individual is going to buy votes in a way that maximizes her expected gain from voting, right? And what's her gain from voting? It's going to be the value she has for the outcome that's elected times the probability that the outcome is elected, which is a function of her voting strategy and the voting strategies of all the other citizens of the country, minus the cost that she has to pay to buy the votes that she's decided to buy. Well, what's going on is that the cost by the quadratic rule is quadratic in the number of votes that she's buying. And the probability of the outcome that she likes is some function of the number of votes. Doesn't really matter a whole lot which one. And so when we solve this optimization problem, we take the derivative, and this quadratic function becomes a linear function. And we set it equal to 0, and we see that the quadratic rule induces each citizen to vote for candidates in proportion to the value that they have for that candidate. In other words, these votes serve as a metric for the value of the outcome. And so the candidate with the most votes necessarily has the greatest value to the society. This idea, as well as many others, is eloquently elaborated in a recent book by Eric Posner and Glenn Weil called Radical Markets. It's a very easy read. I highly recommend it. So they discuss quadratic voting, as well as different immigration policies and property rights and things like that. In the context of that book, as well as some related journal articles, Glenn and co-authors prove this theorem that I sketched on the last slide, that the most valued candidate is going to win in equilibrium in a two-candidate election. This result can be extended to elections with multiple candidates, but both of these points require us to have people buying votes with money. If we want to get rid of the money, instead we can allocate people points that they can spend on candidates. And if there's a lot of choices on the slate, then this point system will induce people to have to make trade-offs between voting for their most preferred and second most preferred candidates. And so the results, it's very technical, but the results of the setting with money will carry over to this setting as well. There's still a big question here, by the way, which I don't have time to get into, but the question is, how do we decide who gets what number of points? Do we want to give everybody the same number of points? That's actually not entirely obvious, because maybe you're a really run-of-the-mill person, so what you want to happen is likely to happen anyway, and we might want to empower a minority group by giving them more points. So the last market I'd like to discuss today is the market for schools, in which I'm going to use raffle tickets instead of money to allocate school seats. And the idea behind using raffle tickets is that you can understand by asking people to risk something. As Calvin says here, you learn how much you value something when you're asked to risk something for it. So we can ask people to risk their seat at one school in order to get an allocation at another school, and that will let us tease apart the strength of their preference for the one school over the other. So I'd like to do a little bit of a deep dive into this setting in the remainder of my time. The results that I'm going to present are asking what's our effective school choice programs, and they're contained in a paper by myself and colleagues Brendan Lucier, Josh Molnar, and Glenn Weil in Wine of last year. The paper deals with a general setting of matching markets, but for the context of this talk, let's just focus on the school choice setting. So in the school choice setting, we have a set of students. These are the kids that live in some city, and each student has a preference over the schools. Maybe you're skilled at art and you'd like to go to a school that has a visual arts program or an orchestra, or maybe you prefer math and you want to go to the team with the school with the good Olympiad teams. And then there's also a set of schools, and the schools have capacities. That is, every year some kids graduate, so they have some vacant seats that they can fill. And the schools also traditionally have priorities over the students. So these priorities can come from things like, you have a sibling at this school, and now the government has decided to give you a priority at that school because it's easier for your parents to drop both kids off at the same school. Or maybe you live within the walk zone of the school. So given this combinatorial structure of preferences, priorities, and capacities, the school choice system asks us to come up with an assignment of students to schools that respects the capacities. I'm going to immediately make two simplifying assumptions that are, I think, fairly weak. The first is that the priorities are generally very coarse in school choice settings. And so I'm going to ignore them altogether and assume everybody has equal priority at every school. The second, which is without loss of generality, is that if a school has more than one empty seat, I can just create multiple copies of that school, and that would be equivalent from the perspective of the mechanism design problem to having one school with multiple seats. So this allows me to assume that there are no capacities. That is, each school has exactly one seat, and therefore what I'm looking for is a matching of students to schools, in which each student is assigned to at most one school, and each school has at most one student assigned to it. So the algorithm that I'm looking for now is a lottery over assignments of students to schools that respects the capacities. That is, no school gets more than one student in my formulation. And so we should think very carefully about what we would like the properties of such an algorithm to be. What are the desirable properties that you want out of a school choice system? So several things might come to mind. Perhaps one of the first things that comes to mind is fairness. This is quite vague. I don't really know what people mean by fairness. But you could imagine fairness means we give as many people their first choice as possible. Or if there are priorities, maybe we don't give someone who has a lower priority a seat at a school where someone with a higher priority wanted it. So there's fairness considerations. Another property that we might want out of a school choice mechanism is simplicity. So we need these parents to be able to navigate this system, right? They have to be able to decide how to interact with the algorithm, what they should state as their preferences. And this can be, depending on how we design this algorithm, this could be a very complicated problem for the parents to solve. One of the postdocs at Microsoft who worked with the Boston City school system to redesign their school choice program was told at one of the PTA meetings that there's no algorithm should ever be proposed that can't be explained to a fifth grader. So I like that as a metric for simplicity. So those are two sort of desirable properties. But the one that I'd like to focus on, in keeping with the theme of this talk, is value. So here, it's difficult to compare across students. How do I know that your kid's, desire to go to school A is stronger than some other kid's desire to go to school A? Comparing across students requires me to make value judgments about the outcome of one student versus the outcome of another student. But I can definitely compare within students. I can say that your value for one school is twice as much for your value for another school. And that's a well-defined comparison because there's a common currency here, your value for a school. Whereas when I try to compare across students, there's no longer any common currency. I don't know how to compare your utils for another person's utils. And so in settings like these, the right sort of metric when you're talking about value is what we call Pareto efficiency. That is, I'm going to look for lotteries in which there's no way to improve the match for some student without harming the other students. Here's an illustration of this definition. I have, and I'm going to work with this example throughout the talk, so it's useful to understand it. I have two students that are triangle types. The triangle type student likes school 1 at a value of 10 utils, school 2 at a value of 2 utils, and has no value for school 3. The circle type student, of which there's 1 in the school system, has a value of 7 for school 1, 5 for school 2, and also 0 for school 3. So they all value the schools in the same way, but the triangle students have a very strong preference for school 1, and the circle students kind of indifferent between school 1 and school 2. Here's one lottery that we can use to assign the students to the schools. I can just do it uniformly at random. Everybody has an equal chance at every school. This gives each person a 1/3 probability at each school, and if you do the calculation, you'll see that the resulting expected utility is 4 utils for each student at each school. But this, if you think about it, is kind of dumb, because the circle student didn't really care whether she went to school 1 or 2, whereas the triangle students had a strong preference for school 1. And this suggests an alternate lottery in which we just give the circle students school 2 and then randomly allocate school 1 among the triangle students. The probabilities in this alternate lottery are 1/2, 0, 1/2 for the triangle students and 0, 1, 0 for the circle students, resulting in an expected utility of 5 for each student, which is larger in a within-student comparison than the prior lottery, which gave each student an expected utility of 4. So the question is, can we find an algorithm that produces this lottery? An algorithm that's commonly used in the school choice literature is deferred acceptance, or maybe you know it under the name of stable marriage or Gale-Shapley. In this algorithm, every student is going to iteratively apply to the schools in order of their preference, and the schools are going to tentatively accept students in order of priority. Now, remember, I got rid of priorities, and so what I'm going to do and what is actually done in practice is random tie-breaking to decide who has priority at which school. So maybe, for example, the circle student has higher priority than the triangle student at the first school, and therefore, in the first round of deferred acceptance, everybody's applying to their first choice school, and the top school prefers the circle student, so it rejects the triangle student and accepts the circle student. Now the triangle student goes on to apply to his second choice school, which in this case is the last one, applies there and has a higher priority than the diamond student, and therefore is accepted, and the diamond student who was tentatively accepted in the first round is now rejected, resulting in this allocation. Now, one thing to notice about this algorithm is that it doesn't ask the students anything about the strength of their preferences for the schools. And so in this setting that we've been studying so far, the students have the same ordinal preferences over the schools, and so they look identical from the perspective of this deferred acceptance algorithm. Therefore, by symmetry, the random tie-breaking rule is going to induce the uniform random lottery among these students, and each student will get a util of 4, which we already saw was not optimal. Can we improve upon this? Here's an alternate mechanism, which is called the Boston mechanism, or the immediate acceptance mechanism in the literature. It's called the Boston mechanism because it was actually in use in Boston school districts until 2005. In this mechanism, it works exactly like deferred acceptance, except that students irrevocably are accepted to the schools when they apply to them. So if we break ties in the same way as before, the first student is going to apply to the triangle and circle students are going to apply to the first school. in the first round. And that school is going to irrevocably accept the circle student who it likes better. Simultaneously, the last school is going to irrevocably accept the diamond student who it also likes better. And so both of those seats leave the market. And what you can see is that by applying to the first school, the triangle student lost her chance of a seat at the second school. So this suggests the following mechanism, which is a simplification of the Boston mechanism. It's like running one round of the Boston mechanism. I give each student a ticket, and each school has a bucket. The students can throw the ticket in the bucket of the school, whatever school they want. And then the mechanism is going to allocate seats by drawing tickets from the buckets. Let's think about how this single ticket raffle, or the first round of the Boston mechanism, operates in our running example. Let's suppose, for the sake of argument, that the two triangle students put their tickets in the bucket of the first school. What should the circle student do? Well, if she puts her ticket in the bucket of the first school, she'll get just over 1/3 of 7, or just over $2, 2 utils. Instead, she could put her ticket in the bucket of the second school and receive 5 utils for sure. And you can similarly check that the triangle students most want to put their tickets in the bucket of the first school. And notice that this induces the lottery we saw was better in the beginning of this section of the talk. That is, each student gets a util of $5. And the basic mechanism at work here is that students have to risk the second choice, their allocation at the second choice school, in order to apply to their first choice school. This lets us prove a theorem, which is that the single ticket raffle is approximately optimal. And in fact, raffles are going to be approximately optimal in any school choice setting, and also, by extension, related mechanisms like the Boston mechanism are approximately optimal in school choice settings, in this sense of Pareto efficiency. And this happens because these mechanisms allow students to express strength of preference through the risks they are willing to take. So in summary, I've discussed these 4 markets: road traffic, online content, presidents, schools, and shown how there's alternates to monetary incentives that can be used to optimize the aggregate value that these markets result in. There's many other markets where we need to run the market without access to currency. Things like public housing, online dating, social networks, cryptocurrency, the market for personal data. That's, I think, going to be a big thing in the future given the recent GDPR laws. And so in all of these settings, I'd encourage you to think about how you can replace monetary incentives with alternatives like scarcity, risk, fame, and time. So that concludes my talk. I just wanted to take a moment to credit all the wonderful 20th century American artists that I used throughout the talk, and also thank you for listening.
So I have actually a quick question. So you have the triangles and circles?
Yes.
So you said the triangles, they have 10, 0, 0, and the circle, it has like 7, 5, or 10, 2. So you assume, so if you change the distribution, you will have very different
For sure, yeah.
results, right?
You will get if you change the distribution, people will change how they act. But because of this fact that you have to risk your allocation at one place in order to apply to another place, this incentivizes them to still act in a way that maximizes their personal gain. So you're still going to get a nearly Pareto optimal outcome.
So 5, 5 are the optimal values, regardless of how you distribute these values? These 10, 12?
I mean, if I change these numbers, then the 5, 5 will also change.
My point is, regardless, like, how do you arrange these? What are the optimal values? 5, 5 will be the optimal at the end?
No, it'll change. Something else will be optimal.
Thank you.
Hi, great talk. I have a question. how do your results extend to benefit over time? So I might make a decision today that has immediate benefit now, but zero later, whereas another decision that has a little bit of benefit today, but it'll have more benefits in the future for everybody.
Yeah, that's a very good question. So, abstractly speaking, I'm looking at a setting where you have a bunch of different outcomes or alternatives you might elect in an election, or schools you might attend. And if you're taking decisions over time, then you can expand the definition of an outcome to include the time at which it happens, and these results will follow accordingly. Now, there's still complications induced by the sort of like, if we take decisions over time, then my action today will give you information about how to act tomorrow. And so those complications are very interesting, for example, in the context of the badge virtual reward systems, and that's an area of active research.
Can you elaborate a bit about the f of v that you had there in the quadratic voting
Sure,
setting? So
yeah.
what's the function of affecting the outcome as a function of the votes?
I didn't specify the function. I want it to be something that's increasing with, let's imagine there's just two alternatives to make this easier to talk about. So now the votes we can, as the winning alternative gets more and more votes, it should have a higher and higher probability of winning. This could be a step function. It could be that so long as I have at least one more vote than you, I win for sure. But so long as it's some sort of increasing function like that, this theorem will follow.
So it's like the probability that my vote will be pivotal for affecting the
Exactly, yes, exactly. So when you do this derivative, I didn't write the proportionality constant here, but that would be the marginal pivotality of a single voter.
Right, so it's like, okay, thank you.